Okay, so for those of you, first thing, there we go. Who's had me before? Okay, a couple of you. Okay, gotcha. So this is 340, evolutionary computation. And one thing I will say, just as a heads up to a lot of people, because a lot of them don't know, who knows what the difference between a 300 and a 400 level class is? It's basically nothing. Right? So if you're like, oh, okay, third year, thank God it's not a fourth year. Sorry, it's the same thing. Like, it's not going to be any different whether it was 440 or 340. What else? For those of you that don't know, so some of you have had me before, some of you haven't. For those of you that don't know, I record all my lectures. That's what this is right here. It's recording. You can maybe wave. See, someone try to wave so I can see a hand. Okay, it looks like I got a little bit of yours. No one else, sorry. Tough, I know, next time. So, and I post them to YouTube. Okay, so you can access them wherever. What else? Professor, okay, you know where the meeting times are, office hours, they're posted here. Here's the link to the YouTube channel. I will make a playlist for each class, so there'll be a playlist for this year's. If you really want, you can find last year's and the previous year's versions of 340 recorded as well, whatever. Course notes, here's the course notes. Student lectures, we'll talk about that later in the course. Student project later in the course. 3 assignments, they're posted, but there's no deadline yet. TBD. I'm trying to think what else. There will be a lot of nuance with this course that'll be a little different from what you're used to, but I'll go over that. But it tends to be really popular with people. This course is designed in a way where there's supposed to be a lot more integration between you and me. There's supposed to be a lot more discussion, more seminar-based stuff. Don't get me wrong, there's lectures and whatnot, but there's going to be a lot of times where I want to talk and discuss or maybe give you an activity to work through for a lecture or something where I make sure everyone's on the same page with something. So it does really depend on your engagement and involvement, and if it doesn't, the course is going to suck. I've been teaching this course for years. It wasn't until last year where I thought it went poorly. Last year was the first year I thought it went poorly because, for whatever reason, last year no one wanted to engage. I don't know why. It was really annoying, which is really sad because to me, most professors, whatever department they're in, they have one course that's theirs. This is the course that they created that's aligned with what they do research-wise, and this is mine. So it was really sad that it didn't go well, so I'm hoping this year, although judging from the faces I see, I'm optimistic, okay? So just keep being good. Office hours, YouTube, okay. I don't remember if in the intro class I talk about the breakdown. Give me a second here. If not, I'll go over the outline real quick just to make sure I hit some of the key points. Pardon me for, Pardon me for the slow, I'm hotspotting because the internet may or may not be working currently. Okay, I'm going to go to the outline real quick. I'm not going to go over the outline in full detail. Come on, you can do it. I'm not going to go over the outline in complete detail. It's your job to go through it, make sure you understand it, ask questions if you have questions, but it's pretty boilerplate. Here we go. Outline. So I'm just going to go over the outline to hit some of the peculiarities. So fall 2024, there are prerequisites. If you don't have the prerequisites and it hasn't been approved, that's a problem. Lecture section, okay, class times, website, textbook, lecture notes. There is a textbook for the class. It's entirely free. It's accessible online. You can download a PDF. Topics. We're going to talk about evolutionary algorithms. Evolutionary algorithms really is this. There are so many layers of categories An evolutionary algorithm is like the top layer. And under that, there's evolutionary computing, which is a subset technically. And then under that, there's like genetic algorithms. And then next to that is genetic programming. And then evolutionary strategy. There's all these different things. And we'll tease most of that out as we go. But evolutionary computation does fit into a broader category of like AI, machine learning optimization, okay? And this broader category is called computational intelligence. And we're not going to really be spending a lot of time on that specifically. We're going to be focusing more on evolutionary computation. But computational intelligence is like a category of AI, machine learning optimization that's like the big guns, okay? It's in the same category as like neural networks. And neural networks are like everything these days. I mean, you go back like 15 years ago, not so much, but they are in that group of algorithms, computational intelligence. These are the big guns. These are the tools you use when nothing else works. You don't want to use this stuff. If you have a problem and you can use a simpler form of AI, machine learning, whatever, to solve it, do it. Do not use this stuff. This is the last thing you want to do. Computational intelligence is a last resort, I got nothing else to try. It's like throwing everything we have at it, the amount of computation, a lot of electricity, and we're just throwing that at a problem. And they really are reserved for the problems where we go, I don't know what else to do. But there is a bad trend in the world of machine learning, AI, optimization, where people do just throw neural networks at every problem. And it's been a joke for like more than a decade, but it still happens all the time. You don't want to have to use evolutionary computation if you don't have to. It's only in those situations where we go, I don't know what else to do. That's when we use this stuff. So that's where this fits in the world. So it's a type of AI, machine learning for optimization, et cetera, et cetera. Things we're going to cover is evolutionary algorithms, swarm intelligence, representations, encodings, common algorithm improvements, application areas, search space analysis, evolving neural networks, and technical communication. We do some of that implicitly. One nice thing about evolutionary computation is it's very modular. The idea of evolutionary computation, like the core principle that turns it into like what it is so simple. It's hilariously simple, I'm going to show you in a moment. It just includes a couple of steps. But how you do each step is entirely up to you. There are things people typically do for each step, but it's modular. You could take that and be like, I don't want to do it that way, I want to do it this way. Okay, cool. People add more steps in there, and maybe they get better results. Good, awesome. There's no hard rules here. That's part of why I love evolutionary computation is you do whatever the hell you want. And a lot of times we get away with like, well, why'd you do that? Because it worked, right? It gave me better results. You try to answer why, but sometimes we don't know because this is really complex stuff. Hard to kind of wrap your head around when we've got these types of problems. So it's very modular. You can do whatever the hell you want as long as you're following the general basic idea, which is really nice. And in spite saying that, you are going to ask me several times throughout the semester, each of you is probably going to ask me, I was thinking of doing the initialization this way. Is that okay? Yes. I can already answer it for you. Yes, yeah, go ahead, do it that way. But if we evaluate our solutions this way, we could go try it, see what happens. My answer is almost always going to be try it, see what happens. If it didn't work, all right. If it did, awesome. Okay, general breakdown of your evaluation. There's 5 things that you're going to be doing. 3 assignments. These are going to be fairly rigid, well-defined things that you do, although there's flexibility on how you go about doing it. There's a final project that, based on the number of people in the class, we're going to have groups, and we're going to have lectures as well. You will notice, if you add up all of these things, so each thing it's out of, maximum points. It's 1% towards your final grade. So nothing's weighted. It's weighted by virtue of having more or less points allocated to it. And there's a total of 115 points you can get. But the maximum grade you can get is technically 99. Meaning you can do everything in this class and get 115, but the highest grade you're going to get is 99. If you get 99 points, you're going to get 99. If you do 98 points, you get 98. But there's extra room at the top. And the reason for the extra room at the top is it gives you the flexibility to kind of pick and choose what you want to do. Because as we'll see shortly, each assignment is, okay, here's the base assignment. And if you do that, you get so many points. And then if you do this, you get more points and more points and more points and more points. So it gives you the flexibility to kind of pick and choose of like, yeah, I really don't care about swarm intelligence. I'm just not going to do as much as this assignment. And you could still get perfect. You really could decide today, if you wanted, like, you know what, I'm going to be really happy with a 75 in this class. So I can pre-plan exactly how I'm going to get that 75, and that's it. Great. I can get 75 by doing, so you have to do the project in the lecture. Otherwise, the highest grade you get, I can't remember if I said 45 or 48, but you have to do these two, but that's 40. If you did literally nothing else, you get 40% in the class. You do one assignment, you get 65. And if you're happy with 65, all right, cool, whatever. Right? So it gives you that flexibility to pick and choose what you want to do. And the reason I do it this way is, in general, you know, for better or worse, when it comes to like our education system, you know, the purpose of a grade is feedback. If you do an assignment and you get 80% on it, you take that feedback. There were mistakes, and you get feedback. It lets you know, you grow and you learn from it. But the reality is that's not how it's treated today. Everyone needs to, like, it's been gamified too much. Everyone needs to maximize their final grade, and they kind of lose sight of like what the point of the grades are. And so this is an attempt to kind of combat that, where like it gives you more ownership of what you're doing, and like usually with courses, everyone starts with like perfect, and you lose marks as you make mistakes. I realize it's effectively the same thing here, but by thinking about it this way, I'm more saying like, the more you do, the more you get. So it's more like everyone starts with 0, but the more you put into this, the more you get out of it. That's the idea. That's the spirit of what this is for. Yeah, what else? And part of it too is, like when it comes to the marking, the assumption here is you can code. You're in 340, you can write your code. Evolutionary algorithms, I'm not going to say they're like trivial, but they're simple. And if you're here and you can't write a genetic algorithm from scratch, after I teach it to you, of course, if you don't have those skills, you shouldn't be here. You definitely have those skills if you're here, assuming you've passed everything bona fide correctly and you didn't weasel your way through. If you did, you're not going to have a good time in this class. So I assume you know how to do this. So like the marker isn't going to be going through your code and looking for mistakes and whatnot. You can write a working GA. The marker is more interested in evaluating what else you did along the way to get those extra points and whatnot. So like no one's going to be going over your code. They'll run it to make sure you didn't bullshit and say like, oh, I got perfect results when you don't even have running code. Yeah, okay, we'll check that. But we assume you know how to write the code at this stage. So I'm not too worried about your code. Assignment breakdown. So here's an example of the assignment breakdown, right? So assignment 1 is going to be like, make a genetic algorithm to solve TSP, traveling salesperson problem. It's a common problem. We'll talk about it in a little bit. If you implement a genetic algorithm for TSP, you get 4 out of a possible 25 points, right? So if that's what I would say is the bare minimum. Get a working GA, right? Now, I'm not saying it should take you a hilariously small amount of time to do it. It's going to take you a while, but getting a working GA, the basics, genetic algorithm GA, that's all you get. Now, if you start adding these enhancements and trying new things, you can get up to an additional 3 points. If you start to solve more complex problems, so the assignment 1 starts with traveling salesperson problem, but there's a harder version called, what do they call it? I can't even remember, but there's a harder version of the problem, a variation of it that's more complex. If you get that working and get good, reasonable results, you'll get an additional 4 points. If you do a good job visualizing results of what you're getting, you can get more points. And a big part of this course is going to be technical communication. It's one of the implicit learning outcomes of the course. That technically isn't explicit, but really you're going to learn it just by doing. You're going to write a report on what you did. I'll give you an example of what they look like, but you're going to write a report. And the reports usually start with an introduction where you explain the problem, maybe talk a little bit about some basic background work there. Then you describe what you're going to do to solve the problem. You show us how it worked, and then you give us conclusions. That's your general report. Now, a lot of students get weirded out, especially computer science students. They get worked up about, oh, I'm going to have to write essays. No. No, 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 no. This is technical writing. This is very different than essay writing. So if that started to freak you out, you could exhale. Right? It's not essays, okay? Because the point with an essay is you've got rhetoric in there, you write nicely, compelling, try to prove, make an argument. That's not what this is. Technical writing, what I usually tell students is technical writing is one step more formal than point form. If you start introducing rhetoric in your technical writing, you're just going to piss people off. If you start trying to be fancy with your writing, you're just going to piss people off. You just say, what did you do? Ba-da. Just list it out. Literally, when I write, what you're going to write is effectively how I would write a scientific paper to be published. And the way I always do that is, I get my results so I know kind of where I'm going with it. But I literally write the paper by saying, I create the section headers, like introduction, background, data, algorithm. I come up with the headings, and then I fill them in point form, what I want to write, what I want to talk about. Pass 2 is, maybe I need to fill in a couple more points, but I just turn the points into sentences that segue and are coherent. And then I'm done. So do not think you need to start trying to impress me with your writing. If you're trying to impress people with your writing, with this technical writing, you're just going to make them mad. Just tell me what happened. Right? How long does it need to be? Okay, well, typically these things are typically you have a double column format. Anywhere from 4 to 8 pages, depending on how much you like to write and your figures and whatnot. But when it comes to technical writing and you start explaining what you did, you'd be surprised how quickly you write 4 pages worth of stuff. It's going to happen pretty quickly. I know a lot of students, especially coming through high school, you're always well, how many pages do I need to write? Usually once you start to get to this level, it flips. How many pages am I allowed to write? Because we don't want a lot of writing. You need to say everything you need to say in as short amount of space as possible. All right? So less is more, assuming it's sufficient.
What's the max for less than?
If you wrote more than 8 pages, I'm going to be very mad at you.
Fair enough.
So don't write more than 8 pages. Don't. Because if you need 8 pages for it, if you need 8 pages, it's one thing if you've got appendices of figures that you've created of pictures and images to go along. That's one thing, fine. But if you wrote 8 pages, you're talking too much. Tone it down. You absolutely could rewrite it with less words. So don't write too much. So if you do the report, you get 4 points. If you use something called LaTeX or LaTeX or LaTeX or whatever, people call it different things. I call it LaTeX. Who here knows what that is? 2 people, perfect. 3, 4 people, amazing. If you use LaTeX with the proper templates, I'll explain more of that in a second, you get more points. If you do proper referencing and whatnot, you get 2 more points. If you include good figures and tables to describe what's going on, you get more points. If you do a good comparison What a good comparison is, though, it's probably more than what you're used to. So like if I just see averages being compared, that's not 2 points. You need to start comparing distributions and whatnot. Who here remembers learning about a t-test? That's like, look, that's not sufficient for the 2 points, but like that would be a bare minimum to be even considered for 2 points. You need to compare distributions. We're going to talk a little bit more about how to compare things as we go, though, so don't worry too much. LaTeX, it is like a word processor type thing, but it's not like Microsoft Word. So Microsoft Word, for example, is called like a what you see is what you get formatter. Like what it looks like on your screen, if you were to hit print, that's what you get. LaTeX is a little different. You use tags, kind of like HTML, but it's simpler than that. And you basically have your whole report written. And let me see if I can show you real quick. Yeah, ad blocker, great. I will say, back in my day, something like Overleaf didn't exist. And you need to like download LaTeX and all these all these dependencies and packages and whatnot. And it was very painful. But now there's a website where it's done all that for you. You just create an account. Maybe I can do this. And it's all kind of like built in there. So you've kind of got like yes, that's me. There we go. So let's see. Here. I'll just show you an example of what like LaTeX would look like. So over here in the middle is what I write. Now a lot of this is boilerplate stuff, so you don't need to be too worried. And I'll give you like samples. Right? But this is how you write it. Like, okay, begin abstract, and then I write end abstract. Keywords, introduction, I write citations in there, so on and so on. But when you like build what you wrote, this is what it looks like. So this is LaTeX, this is like gold standard typesetting tool. And this is how like everything's like done. Yeah.
Does it do this as you go, or do you have to?
So sometimes it will, it depends on how much. Like usually when you if you're like me and you spam like Control S, it'll regenerate every time you save, right? But sometimes you might need to be like, okay, recompile. Yeah. It's a lot nicer now doing it in the browser than it used to be. Man, it was bad before. There used to, you know what blows my mind? There was a time, one sec, I was this is during my master's, right? So this was like Overleaf, I don't think was around at that stage, or if it was only like around for like a year and people weren't using it, and we were all like using it, downloaded. And there's all these obscure tags you gotta learn about, so you'd look them up and whatever. And then my supervisor, she told me, she was like, yeah, well check, and I was complaining about like, you know, I don't know it, I gotta look everything up, it's such a difficult tool to use. She's like, well yeah, check this out. And she walks over to her bookshelf and whips out this book that's like this thick. She's like, well, this is the handbook. Before the internet, this is what you'd use to find it. I was like, whoa, goddamn. Nope. Can you believe that, man? Nope. I'm so glad we get to program like in today's world versus then. Man, if I couldn't just Google something and then have to go through a book where it probably has like a sentence describing each function, you're like, well, that doesn't help me. Anyways, what were you gonna say?
Are you going to give us the format on LaTeX that you
Yes, I think.
Or can we like make our own format?
I think you could probably make your own. In the assignments, I'm pretty sure like use this. I say like use this IEEE one, and then you just import it and you're all set. I feel like I described it pretty well in the assignments, but it's been a year, so I don't remember. When the time comes, we'll make sure it's all good.
Me too, don't be afraid to ask.
Exactly, exactly. I mean, don't ask me. Ask her. Submission, due dates. So those of you that know me, do I accept anything late? No. So a lot of people, this won't be so much for you. You're more senior. But first year students always get really worked up about this, right? Because I know in like high school, there's no lates anymore. So they're not used to this. But first year students get really worked up by this. They'll be like, but I submitted it only 10 minutes late. Yeah, you're right. You only 10 minutes late. It's late. It is. It was due at 11:55. And if you submitted at 11:56, it's late. That's it. There has to be a cutoff time. And let's say you, for example, submitted it. Let's say you didn't have it working, but you were so close. If you had 10 more minutes, maybe you can get something working. But you knew the deadline was 11:55. So you're like, So you submit it before the deadline, even though you know literally 10 more minutes, maybe you would have had it, but you got it in on time at least. And then someone over there took those 10 minutes and they submitted it late. And then I accept it. That's very unfair to you, isn't it? And you know who I do not want to be unfair to is the people that are following the rules. It's only fair if you follow the rules. And let's say you submit it 10 minutes late, and you submit it 20 minutes late, and you submit it an hour late. Well, where do I draw that line? Is 20 minutes okay, but an hour's not? Is 2 hours fine? I don't know. You know what? Let's just stick with 11:55. When I said it was going to be on time or late, that's when we'll make it on time or late. I don't want you playing this guessing game of how late can I submit. No, it's in on time or it's 0. It's simple. And if you think it's unfair, think about the people that you're screwing over by trying to get an advantage. Marking, there's going to be a TA. Project, there is going to be, it's based on the number of students in the class, there's going to be a group project. How many people in a group remains to be seen. It depends when the time comes, how many people there are and whatnot. We'll pick like a project topic early-ish in the semester. But as time goes on, it can switch. I just want to make sure people have a target in mind because maybe like halfway through the semester you realize you're not interested in that, but you're interested in that type thing, so you can switch it up. The project will have a couple of things. There'll be like a proposal. There will be like you do it. And in the end, you have a choice to either do another written report or a lecture about what you did, like present instead. I always thought last year, I assumed everyone would want to present because it'd be easier than writing a report, but only one person presented. So, and then there's going to be a lecture where you're going to lecture for like 20 minutes on a specific topic. Like I was saying about last year, every year before, those lectures were great. Everyone had a blast. The students, everything was well researched. They did presentations. Last year, they disgusted me. They were so bad. I couldn't believe it. And I don't know what happened, but every year before, the lectures were fantastic. The student had fun with it. It was very engaging, very involved. And last year, it was abysmal. And I don't know why, and it really upset me. But like I said already, that's not going to happen this year because I see how enthusiastic everyone is. Email contact, you can email me, office hours. Attendance is mandatory. You can't record me. I own all of the content for the course unless stated otherwise, but don't worry, I record myself. So if you want to record me, don't, but you can check out my recordings. See, it's being recorded. Don't cheat. Yeah, we'll check you for cheating, tutoring, accommodations. This is all the boilerplate stuff. You go through it. It's funny, they always talk about how syllabus, like course outlines are getting too long. Students aren't reading it because they're getting longer and longer and longer, so they need to make it shorter, but every year they give us more stuff that needs to be in it. All right. You'll notice there's no tests or exams. Maybe I should have added them in after how poorly things went last year, but I was hoping last year was a bit of an anomaly. Like I was saying, this content for this course, I'm not going to say it's trivial. It's not easy, but it's simple. And if you're at this, if you've got the prerequisites, you're definitely capable of doing this, okay? So, and like, because there's so much flexibility in evolutionary computing and like how you want to go about solving things, having you write a test for that doesn't really make a lot of sense because it's really do whatever the hell works. This will make sense as we go. So most of the course, it's based on stuff you do. By you do something, you learn something, you get more points, you get a better grade. Any questions from the outline at this stage? Everyone's okay so far? Introduction. This right here, see this picture? Let me zoom out. This is literally it. If I were to write a test, it would be recreate this image, because that's it. This is evolutionary computation. That's it. Now, what happens? Well, you initialize a population. We'll learn about that. We evaluate the population. We'll learn about that. We perform some selection. We'll learn about it. We apply variation operators. Nailed it. And we repeat this process over and over and over and over and over and over and over again until eventually we stop for whatever reason. We'll learn about it. But to give you an example is imagine I want to, this is not the best example, but I'll use it. This one? No, ETFs. What? Why? I guess there's a car called. There we go. Okay, we won't go to it yet. Let me explain. Imagine I wanted to design a car, a little two-dimensional car, to drive along like a road, okay? How do I design that car? Well, I've got to design its like chassis, where the wheel's going to be, how big are the wheels, how big is the engine, whatever. All these different features are going to be important. And I want a car that's good at traversing this space. Now let's hit pause on that for a moment. There's a concept. One thing about this course is it covers a lot of like, and I know this is going to sound cheesy, but it covers a lot of like almost philosophical problems about problem solving that will require some like contemplation on your part to get. So like I can lecture to you about it, but you probably won't be able to wrap your head around some of the ideas I'm going to talk about if you don't think about it. Like some of this stuff won't make sense until you're watching TV one night and you're like, oh, that's okay. Like as soon as you've had a chance to let the ideas brew a little bit. So I'm going to warn you about that. But before I talk about the car example, raise your hand if you walked here today. I don't mean like to campus, I mean to this lecture room. Raise your hand if you walked here. Okay? So everyone here can walk, right? So everyone here can walk. And based on like how we know brains work, there's some encoding in my brain that tells me how to walk. I mean, I'm not even thinking about walking, I just walk, right? So I know how to walk, I can run, right? There is some encoding in my brain that tells me how to walk. And there's one in your brain, in your brain, in your brain, in your brain, in your brain. We all have this. We all know how to walk. But, you know, walking in a physical world, when you think about it, I realize we all do it every day, it feels trivial, but it's kind of a complex task when you think about it. There's balance involved, I got to move a lot of limbs, muscles, tendons. There's a lot going on here. There's a lot involved with walking. It's actually a rather sophisticated, complex task. Yet we all can do it. We've been doing it for decades. So, you know, the configuration in your brain's a little different than mine. So who's better? Am I better at walking than you, or are you better than me? Or is that a stupid question?
Could be subjective.
Could be subjective. I mean, who here's been walking before and you just trip for like no reason? Of course that happens, right? So you suck at walking. Well, no, it's just it happens. Everyone in here knows how to walk. Is there a person on the planet that can be called the best walker? Does there exist somebody that is objectively the best walker? That's probably a stupid question, right? Can you walk? Yes, good. So sometimes when solving a problem, especially when you have these really complex problems, the question of I want to find the best solution for X, sometimes that is a mistake. What you really want to do is find a good solution for X. Maybe your solution is better than mine. Maybe you can walk better than me, but it doesn't matter to me, right? Maybe I can walk better than you. It doesn't matter to you. We can walk. It doesn't matter. So when we have problems where we're using computational intelligence, where things are so goddamn complex that we're whipping out the big guns, searching for the best solution is, in sufficiently complex spaces, is that even a question? Is there even such a thing as the best walker?
Doesn't even make sense.
Is that even a valid question? We would have to define some metrics, but who gets to decide what those metrics are? There's subjectivity to it. So when we're dealing with these complex problems, some solutions might be better than the other, but the whole pursuit of looking for the best solution for a particular problem can often be a useless starting point. Because there may not exist such a thing. There might be no such thing as the best. But there's a hell of a lot of good solutions. So something funny happened a couple years ago, 15 years ago now, maybe even longer. In the world of neural networks, which again, this course is not about neural networks. We're focused more on the computational intelligence side, but there is a lot of crossover here. In the world of neural networks, you go back in time like 15, 20 years, they were not popular. They worked, but they weren't great. People who liked them were like outcasts in the scientific community. They were like useless. They're like, oh, it's like a cool toy, but they're not practical. And in many ways, they were right at the time. But then someone came along and said, what if? Who here's made a neural network before? Done anything with neural nets? One person? Okay, that's fine. When you make a network, like the networks at that time were small. They had only a small number of nodes and layers. That's like how you measure these networks. How many layers are there? And how many nodes are there, okay? And someone about 15, 20 years ago said, what if we make these networks like huge, where we got bajillions of nodes and bajillions of layers? What if we make them huge? And we train the hell out of them. We train them on images of cats to find images of cats on 10 bajillion images of cats. So they've just scaled them up huge. And at the time, everyone was saying, that is a stupid idea. And here's why it's a stupid idea. As you increase the number of free parameters, each node, do I have I think I do. If I were to draw here, could you see over there? Like a network would look something like this. Now, they don't have to be completely connected like this. Like maybe, yeah, and then we've got one output. Great, cool. There's my network. This was like a simple network at the time. In fact, this one was kind of deep because we have several layers. But these were networks were. And each one of these things, each of these has like an input. And then you multiply that input by some weight. This one goes to another weight and gets moved to here. They add them all up. And there's all this fancy math happens inside of it. But what people do, the way they train neural networks, is they go through and they tune these weights. They say, oh, that 0.5 should be a 0.52. And this 0.7, let's lower it a little bit. And over time, as we adjust these weights, it gets better and better results. Here's a picture of a cat. Was it a cat or not? Here's another picture. Was it a cat or not? And by updating these weights, you get better results. So about 15, 20 years ago, someone came along and let's make them huge. Like where this is like hilarious now. Let's make them have so many layers, so many nodes, and train the hell out of them. And so the people came along and were like, that's a stupid idea, and here's why. Because as you increase the number of free parameters that you have, as the number of weights we have increases, the possibility of finding the best configuration is useless. Okay? Like, you ever play like a video game? Sometimes in like puzzle games, you'll have like a knob, right? And you want to find the knobs. You've got two knobs and they have to be set just the right way. But you move this knob and it kind of affects where this knob is. I'm doing a bad job explaining this, but whatever. Each of these things, I have a knob I can control to set its weight. Now, if I have, in this picture, I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I've got 20 weights, I think. If I could have miscounted, doesn't matter. I have 20 knobs, right? Now, realistically, if you've had me before, you know this already. These are real numbers in theory. In reality, they're floating point numbers, so there is a finite number of them. But if these are real numbers, we already know each knob has an infinite number of settings, right? But if I have 20 knobs, think of the number of possible configurations of 20 knobs. Okay? There's a lot. What if I had 200 knobs? Would there be more configurations or less? More, obviously, there's more knobs. If I have 2 million, there's obviously more. So I'm adding more and more and more. It's not possible to create, to find like the best configuration of those knobs. As you add more knobs, it becomes so universally improbable that it's not going to happen. So that's why it's a terrible idea, except it worked really well. And the reason it worked was because like I just said, I don't give a shit about the best solution. As I increase the number of knobs, I've increased the number of sufficient configurations. So it's actually made it like easier because I don't need to find the best configuration. I need to find a configuration that works. And so this is key. So imagine, back to the car example. Any questions about what I just said? Okay, back to the car example. I want to design a car to drive along this road. What's the best configuration? I don't know. Is that even a valid question? I don't know. I just want to find a car that can drive along this road. So how am I going to do it? Am I going to go and design it all? I don't know enough about cars to design a good car for driving along this little road in this physics simulation. So here's what I'm going to do. I'm going to generate 10, 100, 1,000, whatever. I'm going to generate 1,000 randomly designed cars. Okay? I'm going to call that a population of cars. Do you think those randomly designed cars are going to be any good? Probably not. But some might be like less terrible than others. Okay? They're all going to suck, but maybe one gets a little bit further. So what I'm going to do is I'm going to generate the like 100 or however many I said, and I'm going to evaluate each one. And I'm going to take the ones that do relatively good. Like they're better than the others. They're all terrible, but some are slightly less terrible. And I'm going to take them and mix them together and pull them apart and put them over here. And I'm going to keep doing that with, okay, 2 others that are like reasonably good. I could repeat, I could pick the same one again, mix it a lot. And I'm going to put them over here until I generate a new population of 1,000. However, I don't remember the number I picked, 10, 100, 1,000, doesn't matter. I'm going to do it again. That's a generation. And I'm going to do that whole process again. Maybe this time they get, by taking those that were kind of good and mix them together and pull them apart, maybe they get a little better. Maybe they get worse. I don't know. Let's do it again. Take those that are kind of better and put them over here. Do it again. Repeat this process 100, 1,000, 1,000,000, 1 billion times. And at the end of the day, you get pretty good results. And here is an example of a similar thing. Of course, it started with a reasonably good one. Let's just zoom in. Oh. You know what? I'm going to refresh because it had too much of an outlier that it kind of made it boring. But we randomly generate cars. That one's actually pretty good. I'm getting unlucky by getting lucky. I'm starting with too good of a configurations.
How many cars are being generated?
I think it looks like 20.
20. Yeah, you are like Really unlucky by being.
Yeah. Usually they start off with worse configurations.
Yeah.
But eventually they all die out, and then you start over again. The blue one is the elitist one. That was the one that did the best last time. And everything else was based on what worked reasonably well the previous time. And if we repeat this process over and over and over and over and over again, the cars get better and better and better and better. That's evolutionary computation. Now, how did we initialize the population? Well, we did it randomly, but we could do it however the hell we want. How did we select those that were better than the others? Well, here I'm guessing it's just based on how far it went, but we could do it however we want. How did we, like when we picked the good ones and we mixed them together and pulled them apart again, how did we do that? Well, however we want. And when do we decide to stop? Whenever we want. So this has made some design decisions on how to build their evolutionary algorithm. But at the end of the day, there's a lot of flexibility, a lot, in how you go about doing it. Looks like the blue one. This looks like we just got, let's try one more time.
Really lucky.
We're going to try one more time. I really hope we start with just terrible ones. There we go.
There we go.
See, they're not very good.
Long enough.
They're not very good, but
Oh my gosh, that one's still going.
oh, look at this one. It's got a little like, yeah, that's fun.
A little tail.
What's neat too about evolutionary computation is the creativity it comes up with, because it's not bound by what humans,
Logic.
but it's not bound by like what we think a good design would be. Like that worked. Look, it's still going. Like, who would have designed that? No one. There are examples of like little antennas that were designed with evolutionary computation that are on like satellites. No human would have designed the antenna. It's absurd. It's shaped like, it's a crazy thing. And it's tiny. And it's this antenna. Imagine taking a paper clip and just kind of like bending it in arbitrary directions. And it somehow being magically a really goddamn good antenna. A human wouldn't have designed it. But this is hilarious. Look at that.
All this
Wow.
reminds me of is,
Oh, no.
This only reminds me of Code Bullet on YouTube.
Oh.
Like, that's the only thing I'm thinking of whenever I'm seeing this.
Anyways.
So how does it get better?
Pardon?
How does it get better each time?
How does it get better each time? This is a big concept we're going to be talking about over the course of this semester. And it's hard to explain right now without the context, but in the first few topics, we're going to go over how this can happen. There's no guarantee that things get better, but empirically, on average, populations increase in fitness. Fitness being how good they were at solving their problem. So it starts, so this particular example isn't a genetic algorithm. I believe it's an evolutionary strategy which only incorporates mutation, but basically what they're doing in this particular situation,
Mutation-based?
yeah, I think so. Basically you take a car that was good, and you're like, okay, this was good. I'm just going to change one feature of it. Let's make the wheel bigger. Try again. Okay, that didn't work. Make the front wheel smaller. Did that work? So it's just small modifications. And it's all, now, computer scientists, when doing evolutionary computation, are very careful. They don't like to use the word random, but they do like to use the word stochastic. Does anyone know what the word stochastic means?
No idea.
It means random. That's not a joke. I'm being serious. Because randomness there's something called a random search, and people will sometimes be like, that's just a random search, but it's not. So they don't use the word random, they'll say stochastic, but it means random. Everything in this is all probabilistic. Did they get selected for mutation? What type of mutation? It was randomly generated. Yeah. So like, I'm guessing the yellow one is a slight variation on the blue one. The blue one was the elite one.
The wheel is slightly bigger.
It's hard to tell, but that's, and they only get better by virtue of the selection process. This is the core concept of the course, so we're going to hit that a lot more. Any other questions before we wrap up today? All right, cool. All right, we'll stop here for now. But I'm really not joking when I say this right here is the whole course. That's it. Everything else is more details about this specific thing. All right, I'll see y'all Friday. I think Friday.